finally be able to introduce Josh Peep. It's been a couple of semesters. We tried scheduling you, and then we had to reschedule. And anyway, it's really, really great to have you here. He's an expert on gas, multi-phase gas in particular. He's currently an assistant astronomer at Space Telescope. He got his PhD from Berkeley. Then you were a Hubble Fellow at Columbia. And decided to stay on the East Coast and now at Space Telescope. So great to hear what you have to tell us about tomography today.
Thanks very much. It's been really fun so far. I'd love to be able to give a talk in the middle of the day so that we can talk about it at the end of the day. I'll be talking today about tomography, edge of tomography. I feel like we're making a lot of big progress right now in astronomy in tomography, so I'm hopefully going to be able to give you some ideas about that. If you haven't figured it out already, I talk kind of fast. First, let me just say, Kirill Chernyshov is my graduate student who a lot of the work, especially at the end of this talk, will be about his work. As I say, I talk kind of fast, and I also have this great, this slide has the most words on it of any slide, by like a factor of a lot. But I'm going to leave this at the top of the slide. So if you lost what I'm saying, you can kind of ignore me and then just read at the top of the slide, and you'll get basically the major point of what I'm trying to say. And hopefully they will be statements, not, junk or something like that. Okay, good. So astronomy has always been this science of catalogs. This will be the earliest citation I use from Ptolemy 155. But we have this extreme advantage over many other sciences, which is that it's very easy for us. We have this black sky. This black sky is this extraordinary resource because the stars at night are big and bright and so forth. And we can see them as separate entities, right? And so then we can turn them into rows and columns, and then we can do statistics on those rows and columns, and we can learn a lot about the universe by turning our data into these kinds of rows and columns of data. But the universe is actually mostly diffuse, as you've probably noticed. Most of the universe is dark energy, so diffuse we don't even conceptually understand it. Dark matter, which is very diffuse, people have sort of thingified it into halos, but if you really think about dark matter, obviously it's this continuous field of material. And then most of the rest of the universe is in this plasma and gas with this tiny leftover fraction of things that are stars and planets and black holes and the Millennium Falcon and whatever else. So it's critical to understand this diffuse stuff, but it really doesn't fit into that same format of rows and columns. It's very hard to thingify and to apply sort of what we think of as statistics to it. But I think more importantly, not that there's just so much stuff out there, but what we've become interested in over the course of time, as I'm going to demonstrate here, is formation. So on the x-axis is decade, and on the y-axis is the number of times the words star and formation are used both in an abstract of a paper on an ADS. It's divided by the number of times just the word star is used. And you can see this upward trend, which is that we've stopped just wanting to catalog the universe. We're not really interested in just how many stars there are. I don't know if, when you tell somebody you're an astronomer and they say, oh, you discovered a star, and you're like, it's not really the important part. The important part is formation. We want to know where things came from. Now, I can't motivate my talk any further back than this. I don't know why we're interested in where we came from, but evidently we are. I sometimes show the NASA budget and show how much we're interested in cosmic origins. Putting your money through backwards. But obviously this is a topic of interest. And if you want to understand how the universe came to be the way it is and how everything formed, you basically, the simplest thing you can say is that diffuse stuff became dense by gravity. That's the 0th order story of how everything formed. Now, we know that's not the whole story, but we know if we want to understand formation, we've got to understand this diffuse stuff. We also know, what we've learned, especially in the last kind of 2 decades, decade and a half, is that this formation is deeply entwined with destruction, right? Molecular clouds get built in the galaxy, but only maybe a few percent of them actually turn into stars. The rest of them somehow get destroyed. So we know there has to be some kind of low efficiency that happens when we're building molecular clouds. And that's what I'm showing here on the left side is the Rosette Nebula, where it's blowing up. There's all these molecular clouds over here that it's blowing up into, and we know that that feedback process is really critical for understanding what's going on. And the same thing is true, obviously, on the galaxy scale here. I always say that the Union of Circumgalactic Medium Astronomers requires that you show this image of imaging every time you talk about feedback. Obviously, not all galaxies look exactly like this, but I'm just making the point that the amount of baryons that exist inside of stars is very small because there's some kind of process that's returning energy and material back out to the circumgalactic medium. And so not only do we need to learn about formation, but we need to learn about destruction if we want to understand how formation works. So we need to really understand how flows work in 3 dimensions in the galaxy and in the universe as a whole. So how are we going to do that, given that all of our data comes from these point sources? Well, I'll tell you two ways, and I'll talk about both of these ways during my talk. You can just study this diffuse universe through absence, okay? So this is a Bok globule where you're seeing a lack of stars. and people originally studied dust, this intervening sooty material that blocks our line of sight, by looking at absences in catalogs. And you can look at that absence both in objects, but you can also look at it in these absences in terms of their absorption. So these are diffuse interstellar bands that you can see in apogee data, I think, at high resolution. And you can see them here blocking out the light. And these diffuse interstellar bands are associated with some kind of intervening material. And I'll talk about both of these processes a lot during this talk. But generally, the point is that if you have photometric observations or spectroscopic observations, the absorption out of those observations tells you something about the intervening material that's really useful. Okay, so the talk is going to be in these 4 sections. Let me go a little fast, we'll see how it goes. First I'll talk generically about dust and tomography. Then I'll sort of talk about the sort of 0th order version of tomography where you're just asking about a single screen. How can we measure a single screen, and how can that be useful for doing cosmology and for studying the rest of the universe? Then I'll talk about going into 3 dimensions, when you think about building a 3-dimensional map of gas inside our galaxy, and then I'll take you beyond the 3rd dimension. And hopefully that will be exciting and interesting and new.
Sounds very Buzz Lightyear.
Yes, very Buzz Lightyear. This will be the Buzz Lightyear portion of the show. Okay, so first dust and tomography. So just to get started with dust, if you're not familiar, basically much of interstellar metals are in dust, and they trace all of the gas in the galaxy. They're very well mixed in, at least in our galaxy, with the gas, and they're a product of evolution, right? Everything in a dust grain was generated in a star, and so in some sense they're a tracer of stellar evolution. This is, most of the metals, as astronomers call them in the universe, are these. And of these are very highly depleted onto dust grains, which is to say that most of the oxygen, carbon, silicon, and so forth are all depleted onto dust grains, and they're not in the gas phase. It's only these nitrogen and neon that actually exist mostly in the gas phase. So if you want to study where the metals are in the interstellar medium, there's quite a lot of them that are actually in little tiny rocks. Now these dust grains, we don't typically just go out and pick them up. I think we have like 3 interstellar dust grains that we've collected from satellites in history of time. So the way we really do this is with extinction. So we see that dust grains extinguish light more towards the blue and the ultraviolet on this side here. So I'm just showing you the standard extinction curve. And this extinction curve can be parametrized in a number of different ways. The classical way it's parametrized is by the steepness at this point here, at this inflection point, which is called RV, which is just basically how much blueness do you get? How gray are the grains, or how blue are they? And just to give you context, this is the WISE band. This is the Sloan colors that you're going to be familiar with, UGRIZ, and this is Galax colors. And so you can use, by looking at background objects, you can try to measure this reddening curve. And I'll be talking about that significantly through this talk. So the steepness of this curve tells you something about how the grains work. It could be that the flatter curve here represents larger grains. And as you get to smaller grains, you get much more steepening from e-scattering. Okay, so let's talk about tomography. I told you about dust. We're going to be using dust a lot to do tomography. But now let's talk about what do I mean by tomography. So classical medical tomography is basically you have these slices of data, and you slice 1 and slice 2, and you try to reconstruct this 3D scene. And it's kind of gross, but so we don't have these slices. We can't go out there and make slices of the universe and rebuild the 3-dimensional universe, but it's kind of cool to look at. Stellar tomography, and I won't be talking about this at all, is just trying to go from a 0D object, i.e. a point in space, and look at the 3-dimensional distribution. And so some folks have used Sloan data once again to look at the distribution of stars in the halo, and maybe you can see the monstrous stream down here and what have you. But this is actually looking at where the stars are, not looking where the intervening material is. So gas tomography is looking at the dimming along the line of sight. So here's the sun, and this is 100 parsecs. So this is the local stellar neighborhood. This volume is called the local hot bubble. If you're interested in this, I've written too many papers on this topic as well. And what people have done is used the sodium-1 absorption, remember I talked about absorption from the gas lines, as a way to measure the intervening gas to all these little blue dots. You can't really see them, but there's a bunch of blue dots on here in this image. And those blue dots are where the stars are, and if you see sodium-1 absorption along the line of sight, you know there's got to be something here, and so you can use some algorithm to rebuild what you think the 3-dimensional structure is by going from these spectra to this 3D volume. But you can also do it in extinction. So if you basically ask, I see a star, I expect I know how red it is, it looks redder than that. That tells me how much dust is along the line of sight, then I can do the same thing. What's nice about this is since photometry is much cheaper than spectroscopy, you can do this with many, many, many stars. I'll be talking about this at some length. But this is sort of what the state of the art was in 2011. And I have a colleague, Carl Gordon, who sort of sits in the same group at Space Telescope, and whenever I talk about this tomography stuff, when I came to Space Telescope and I told him I did this, this is what he said. He said, so what? So you've got a three-dimensional map at really low resolution of the nearby area around the sun. So what? Why do I care? Why is this interesting? And I didn't have a good answer to that question. But I think I do now. So I'm going to invoke Carl a couple of times as I talk about these three-dimensional maps and hopefully convince you and Carl that this is interesting. And that there are really interesting things you can do with this. And we're just coming to the point where these maps are coming to their fruition and we can really do a lot with them. Okay, that was Dustin tomography. Now I'm going to start on standards and maps. So what can we do with tomography in just 2 dimensions? Trying to reconstruct a single plane. How much dust is there between me and infinity? So I haven't talked about this much, but the classical way you build these dust maps, which is critical for cosmology, is to look at the far infrared emission from dust grains. So the dust grains are suffused inside a radiation field that comes from stars. And those stars heat up the dust grains, usually in the ultraviolet or optical, and then the dust grains re-radiate in the far infrared. And all the dust grains are all about the same temperature in the Milky Way, somewhere between 16 and 18 Kelvin, say. And so you can make these beautiful maps of the far infrared. This paper has almost 10,000 citations. Why? Not because it shows you where all the dust is in the galactic plane, right? So this is galactic zenith, this is galactic anti-zenith, but where it shows you where the dust is at high galactic latitude. This is the Sloan footprint in the main galaxy survey. And it actually matters more where in the regions where there's very little dust, how much dust there is, because this dust is really influential in trying to measure cosmological parameters. So this next chart is a little confusing, so I'm going to walk you through it in some detail. So imagine you're doing a large-scale survey, say for baryonic acoustic oscillations, and you're trying to do your target selection. Well, you need to find targets that go to some uniform depth. You assume you're going to go to 19.1 magnitude or something. Imagine that your dust map is wrong. Imagine you guessed incorrectly what your dust map is. So that map I showed you from Schlegel, Finkbeiner, Davis gave you the wrong answer by some level. Okay, and let's assume we know what the known. Let's assume we know that now. Now let's forward model this whole process. How do those errors propagate into our data? Well, if you basically look at the faint end slope of the luminosity function, basically how many galaxies you get as you go to fainter and fainter, that maps pretty well onto redshift, and so I put it as redshift here. So for different redshifts used for the cosmology, you get some amount of bias as a fraction of the amount of error you have. Okay, so how biased are your data? And clearly, you don't want your error. There's really no reason to do any more observations once you're dominated by bias, right? And this is the dominated by bias regime. And you can see you become dominated by bias when you're trying to measure some version of non-Gaussianity or some measurement of the change in W with time. Once you get to certain levels of error and certain looking at certain redshifts. So for instance, if you're trying to do this with LSST, you get into real trouble. You don't know your dust map really, really well. So we've gotten to the regime where we're doing cosmology so accurately that we actually are now limited by our accuracy in our dust maps. So hopefully I will motivate for you why I want to build really, really accurate dust maps at high galactic latitude. Some quizzical looks in the audience that you can ask me. Okay, so you know what a standard candle is, right? A supernova, a standard candle, something of known luminosity whose brightness tells you its distance. And you know what a standard ruler is, a baryonic acoustic oscillation is an example of that, something of known physical scale in the universe, so its angular scale tells you something about its distance. Well, I'm going to be talking a bit about standard crayons today, something of known color, that when you see a different color for it, you know that there's some kind of intervening gas. So what did we do? We took a bunch of quiescent galaxies from Sloan, now 5 years ago, and we selected them spectroscopically. So we basically asked for all the spectroscopic galaxies we have. So there's 800,000 spectroscopic galaxies, and we just look in this little tiny corner where there's no oxygen 2 emission and no H alpha emission, which turns out to be a very good proxy for galaxies that are no longer forming stars. Well, galaxies that are no longer forming stars are really, really delightfully boring looking, and all of this, which is just excellent as far as I'm concerned. And why that's excellent is that as long as you know their redshift, which I do because I have spectra, and as long as you have some idea of what their absolute magnitude is, which you gotta know because I have their spectra, I can measure their color with ridiculous accuracy. And once I regress out those two effects, this is what the color distribution looks like in G minus R in log. So you can see this is a Gaussian fit, this gray parabola. And I have an error, a 1 sigma error of 24 millimagnitudes. And that means for a small patch of sky where I have a few hundred galaxies, I can average them all together and get down to 1 millimagnitude precision in terms of my reddening. So if I want to figure out what's going on along the line of sight, I can do that. And so that's what we did. And we asked, how well do the standard dust maps work? And the answer is pretty well. This is galactic zenith. It's towards galactic hazy center, towards galactic center. This color is Schlegel-Finkbeiner-Davis is completely correct. This black line is they're off by 3 sigma, and this red line is they're off by 3 sigma in the other direction. So you can see there are areas of sky where they do bad, they don't do so well at the sort of 2-3 sigma level, and some areas where they do really terribly. This is off by sort of 40 millimax.
So the errors are in the EBV.
Yes, this is an EB minus V color. That's exactly right. So it's this map that was used in that original diagram that I showed, where I showed how this influences cosmology. So it's critical that we can make these kinds of tomographic maps by using background tracers rather than just using far infrared emission. It turns out there's an error in how the temperature is being used to calibrate the far infrared maps that we think is generating this error. If you remember back in the bad old days, before far infrared measurements, people used H1, neutral hydrogen emission, and the 21 centimeter line, as a measurement of extinction. And that turns out to work pretty well. So this is what the original SFD map sees in terms of the amount of extinction, same area of sky. This is what the Leiden Argentina bond survey sees, that's neutral hydrogen emission of the 21 centimeter line. And this is what we found with our background galaxies. So one question we can ask is, which of these is better, right? Is this map using the H1 or this map using the far IR a better proxy for the actual extinction to galaxies? And what we find is that they both do pretty well. These are on the same scale, so this is just the difference. So if I use H1 to get to extinction, or if I use far IR to get to extinction, which is better? What we find is that these look pretty similar, but interestingly, they have errors in different parts of the sky. And it turns out those errors cancel at some level. And so in the future, if you want to build a really nice map, and I think this is true, that in the end, when we build our final dust maps, we're going to want to build some combination of far infrared emission and H1 to get the best fit to the actual data in terms of extinction. So at least we've learned a little bit about how to make these really good dust maps if we want to do cosmology and the optical into the future. Okay, so I talked about dust here. That was the sort of service portion of the show, right? Not that exciting, but really important if you want to do cosmology. But dust is also important cosmologically outside of galaxies. So you're probably used to things like omega matter, omega lambda, whatever, these things that are the energy density of the universe as measured in some kind of component. Well, I'm showing you here omega dust, which is the energy density of the universe in dust. And we measure this in 10 to the minus 6s. I'm not going to tell you that most of the energy density of the universe is dust, though that would be hilarious. And a number of authors have found something really interesting, which is that the dust inside galaxies might be a few 10 to the minus 6 omega dust. But the dust outside galaxies, in the halos of galaxies, in the circumgalactic medium of galaxies, is also comparable, which is to say there's just about as much dust outside of galaxies as inside of galaxies. When I say outside, I mean 50, 100, 200 kiloparsecs. So really far from galaxies. We're not talking about the surface of galaxies. And the way this is done is you look at background objects of some kind, quasars in this case, and you say, are they redder when they are nearly behind a background object? So you basically do a two-point correlation function between a foreground galaxy and a background quasar. And you ask, how much does the quasar get redder? Now we can do the same thing using these standard crayons, and what's nice about this is that with these standard crayons, our foregrounds are also spectroscopic galaxies from Sloan. So our backgrounds here are these crayons at this range of redshifts, and our foregrounds are these spectroscopic selected galaxies from Sloan at this range of redshifts. And so what's nice is we actually know a lot about these galaxies, right? People have done tons and tons of work on these galaxies, and so we know things like, for instance, their specific star formation rate and their mass. Okay? So you've probably seen these diagrams before. This is the so-called red sequence, the so-called blue cloud. These are things that are forming stars really quickly, spiral galaxies, etc. These are red dead galaxies. People spend hundreds of colloquy arguing about this particular diagram. I'm not going to do that. I'm just going to point out that we can now ask, not only is there dust floating around galaxies, but is there dust floating around blue galaxies? Is there dust floating around red galaxies? Floating around massive galaxies? Floating around low mass galaxies? We can actually split these samples up and ask specific things about the dust and how it relates to the process of galaxy formation. So instead of just saying cosmologically there's lots of dust floating around in deep space, we can ask, how did it get there? And why is it there? And how long will it last? So we did this experiment, and we basically see that there seems to be a lot of dust inside about 150 kiloparsecs. This previous experiment didn't really have a lot of sensitivity to impact parameter, This was just sort of a guess. We're seeing something pretty similar to what they see, but we see actually a sort of an increase inside 150 kiloparsecs, which is kind of consistent with what people see in terms of metals when they look around galaxies in the circumgalactic medium. How much metallic carbon or metallic oxygen is there in galaxies? There's kind of a cutoff that happens around 150 kiloparsecs. What we find very interesting, I think, is that yes, if you look at an L-star galaxy, so a galaxy like the Milky Way, you do see more reddening, so this is our reddening curve. You do see more reddening than when you look around a small galaxy, something a 10th L-star, more like the LMC. But you only see about a factor of 2 more reddening, okay? And if you look at a high specific star formation rate versus a low specific star formation rate galaxy, you see just about the same, which is to say they have the same dust halos. They're kind of identical. And this is really interesting because you would expect that a big galaxy would have a lot of dust, and a small galaxy would have a little amount of dust, but naively you'd expect they'd kind of scale 1 to 1, right? There's sort of 10 times as many baryons in an L-star galaxy, but the dust only goes up by a factor of 2. What this allows us to do is actually account for all the metals ever produced by stars. So if you look at the stars that are producing metals in the galaxy, you can go try to track down senses of where all those metals went. And for a long time it's been confusing because nobody knew where those metals went. And what we're finding is something really interesting. So this is the mass of a galaxy from about 10th L star to L star, so LMC-sized galaxies, Milky Way-sized galaxies. And this is all the metals that have ever been produced by those galaxies based on looking at the sort of star formation history of those galaxies. And so this is all of the metals. This is accounting for all of the metals ever produced, and this is accounting for none of them. And this black line tells you what we've ever been able to find inside the galaxies themselves. So this is the missing metals problem. Basically, only 20 to 30% of the metals that we've ever produced by a galaxy are found inside the galaxy. Work by people like the Cos Halos team have found that there's a lot in the circumgalactic medium around galaxies, but what we found is there's also a lot in dust. And consistent with them, we find that we're able to reproduce this more on the small scale, right? Because I said that a small galaxy only has a little bit less dust in its halo than a big galaxy. And so by fraction, it has quite a lot of dust in its halo. And so we're actually able to almost solve the missing metals problem here. This is almost an astronomer speak. So only a few tens of percent off on this side, but here we're really failing. We really don't know where all the metals went in the L-star galaxies. So this remains an interesting open problem, but we've sort of filled in a chunk here where we're starting to understand that on small galaxies, we're starting to find where all the metals that those galaxies ever produced.
So this is redshift 0.
0.05. So very low redshift. It'd be cool to do this at higher redshift, and hopefully we'll do that with stepping first. Okay, so let's go back to the galaxy. I've taken you on a wild journey around in cosmology land. I promise to never do it again. And I'll bring you back home to the galaxy, and let's talk about actually building dust maps in 3 dimensions, back to this concept of tomography. So we did 2 dimensions. We looked at how much dust is there on the plane of the sky, either around the galaxy or on the surface of our galaxy. Now let's go back to 3 dimensions. So up to 3 dimensions. So the critical idea is that we're entering this era of tomography machines. Telescopes that are going to generate so much photometry and spectroscopy that we're going to be able to do incredible tomography. So Pan-STARRS has done about 1 billion stars. We're going to be releasing this data at Space Telescope actually rather soon. We don't have much parallactic information to them, and the data are available now. Apogee is part of STSS4. They're doing high-resolution spectroscopy, our 23,000 spectroscopy, so they're able to resolve out the velocities of features. Many fewer stars with no parallax, but also available now. And I'm going to be talking about these 2 primarily. But I'd just like to point out that Gaia is going to be giving us ridiculously precise parallaxes. And soon you're going to be seeing these incredible papers where people are building very precise 3D dust maps in the local volume of the galaxy. And LSST, of course, is going to be spectacular for this with many, many, many more stars, much deeper into the galaxy. And actually will also have some parallax. And so putting these things together is really going to be spectacular. I'm going to focus on this Pan-STARRS and Apogee data. I'm going to switch back and forth between different projects involving Pan-STARRS and Apogee. And I'll put down in this lower corner which one I'm talking about, because it's going to get a little bit confusing as I switch back and forth to try to move forward in a scientific direction. Okay. So 2 different large data sets that we're going to be able to use to figure out where the dust is and hopefully learn something about the difference. So the way this is done with Pan-STARRS data is sort of a simple idea. You have some guess as to what's going on in, say, a color-color diagram. So here's some stellar locus, and you make some measurement over here. And so maybe you're, and this is the reddening vector. So if you have more and more dust, you push in this direction in this space. So more dust pushes you this way. So maybe you had this much dust and you were this kind of star, or maybe you had this much dust and you were this kind of star. And if you look along, and so you can think about this as basically a 2-dimensional probability distribution function for both the distance modulus, and the dust. And so for an artificial star test, you'd see something like this. This is work by Greg Green. So on the x-axis here is distance modulus, the y-axis is extinction. This was the true data point, and this is, once you propagate it through the model, sort of where your PDF lies for the data. So the idea is you combine all of these together, and you end up with, along one line of sight, so you say along one line of sight where there's 1,000 stars, say, it's a little tiny patch, you say, I assume the dust is kind of the same, and this is what you find. That when you multiply all those PDFs together, you end up with something where you can actually predict that, there's a cloud at this particular distance modulus. Because stars behind here typically saw some reddening, and stars up here did not see some reddening by taking all of these PDFs and adding them together. You can think of this as sort of a Bayesian version of a main sequence fitting or something like that. Okay? So for each star, you make a guess as to whether it's a red giant that's really far away with a lot of dust, or a main sequence star with very little dust, or what have you. So they have to, of course, have some Bayesian prior about what they expect for stars and where the stars are distributed in the galaxy and so forth. And that's a nice work by Greg Green. So this allows us to build this 3D map, right? This is 1 pixel, and I say, as I go in distance, I see this much dust, and so this is I take these and I do this for every pixel in the sky, and yeah, I have a 3D map. And then Carl says, so what? So you have a 3D map. Well, I'll tell you, Carl.